All right, everyone, we are back and we are going to on to question 2, Bragg bubble raft. So we have this cool apparatus, different sizes. Basically, you're compressing this bubble raft. You have a force transducer here. Oh, I need to charge my pen. I'm going to do that today. An adjustable stage. It compresses the bubble raft. There's a piezoelectric here, and as you compress and apply a force here, you read basically this output. And then there's a pendulum. We actually calibrate it with this mass. So we have this bubble raft of width W, 2 plates, initial length apart, force converter voltage. Force of the pendulum is described as such, and we use this force in order to calibrate our system. So we calculate this force correlation factor, FCF, which is just the force divided by the voltage. So our force is equal to mgx over h over voltage. So this is our fundamental function, FCF. So let's go ahead and let's start to bring up Mathematica. And let's start to look at this uncertainty analysis. That's right, you guessed it, error propagation. So we're going to see that right now. So let's go ahead and wait for Mathematica to open. There we go. It's waking up. It's waking up just like we're waking up. So our FCF is equal to m times g times x divided by h times v. Let's go here. So we're told that the mass of the nest was measured 10 times. So nm, number of mass, is equal to 10. The xm is equal to 320 milligrams times 10 to the minus 3, or 10 to the minus 6, actually, because we have to do kilograms. Standard deviation of 1 milligram, so equals 1 times 10 to the minus 6 kilograms. Good. We found the X voltage was equal to 4 volts. The S voltage was equal to 1 times 10 to the minus 3. What else do we got here? Sample standard deviation, sample mean, nominal value of X to be 5. So this is our XX is equal to 5 times 10 to the minus 2. Nominal value of the height to be XH is going to be equal to 20 times 10 to the minus 2. All right. We used a really bad ruler and where we could best resolve. So we have an uncertainty in the X, which is 1 times 10 to the minus 2. We have an uncertainty in the height, which is also equal to the uncertainty in the X. We have an uncertainty in the voltage, which is equal to 1 times 10 to the minus 6. All right. Are we told mass of the nut was measured 10 times? Mass of the nut and the voltage was measured 10 times. So we also have a number of voltage is equal to 10. All right. So let's see what we've got here. So let's go back to our function. So we have parameters mass. So let's go ahead and we have bias precision. So we could have voltage. We could have gravity, X, H, and mass. mg, x, h, v. Good. Gravity, neither. Bias in the voltage, yes. Do we have precision in the voltage? Yes. What about precision in the mass? Yes, because we're told how many times. Height in x, no precision, but we do have bias. Do we have bias in the m? Bias in the m. We don't have bias in the m. Do we have bias in the voltage? Yes, because we have an uncertainty there. So let's go ahead. So we're going to define. So we have precision in voltage, which is just going to equal to T of 0.05 because we're at 10% significance. and we're going to do S of voltage over square root of N voltage. And that will also have precision in the mass, which is going to be T, and then the degrees of freedom is going to be 9 because we have 10 measurements, so T.05 and 9 S of M over square root of N M. Excellent. So let's find that T05 nu of 9 equals what? And actually, let's go ahead. T of 005. T. Finish this quickly. T of 05 is N9, 1.833. 1.833. Good. So we can have precision in the voltage, which is going to be equal to T05 nu times standard deviation of voltage, just a little SV, divided by square root of NV. We're not envious of this task. Pun. Dun-dun-dun. XV. We want to normalize by this. So we could also do precision error in the mass as well. SM, NM, XM. Good. So now we have to look at our bias. Okay, let's go ahead. Let's look back at our... So we had bias in the voltage X and H. So let's go ahead. Let's move over here. So we have bias in the X. So actually, let's do DFCF dV is equal to derivative of FCF with respect to V. And we'll also have the partial derivative DFCF with respect to derivative dx, derivative FCF x, and we have DFCF dH equals derivative of FCF with respect to h, height. And we didn't have any information about the... Yeah, we're not given any information about the other ones. All right, so let's go ahead and let's put that in there. So my bias is going to be, my bias in FCF is going to be equal to square root of DFCF dV times uncertainty in V divided by FCF squared. And we're going to take that and we're going to add it plus boom, and then boom. So let's plus. So instead of X, H, let's do slash dot. H goes to XH, V goes to XV, and X goes to XX. And there we go. Let's look at this numerically. We've got it. So my total uncertainty is going to be square root. Let's do square root of my PV squared plus PM squared plus BFCF squared. So what dominates? Clearly the bias, for sure. How can we improve it? Well, why don't we use a micrometer next time? And that would definitely, micrometer would really help us in that area. So that's it. Fantastic. Problem 2 done. Contingency tables are next. We'll see you then. Thanks.